is just simply equal to 4. And so I would be able to plug in a 4 for that value there. And so what I'm starting to see is I'm starting to see a trend. I'm starting to see this graph is getting higher and higher for every 1 point over that the x goes. So when I'm generating test points, usually what I'm doing is starting at 0, and then moving one x value over each time and trying to figure out where or how the y value is being impacted. We're going to do one more. Let's try x is equal to 3. And so when I plug that into the equation, y would be equal to 3 squared. And then that would mean that 3 squared is 9, so y would be 9. And so I would be able to graph a point all the way up here. So we're starting to see something. We're starting to see that this started really, really small. And then as this is increasing, this is just going to keep going up and up and up forever. And we would assume it would just keep getting bigger and bigger differences in the y value. And so I'm a little bit confused right now with what this point is. And so what I'm going to try to do is I've been moving to the right with my x values. Let's try moving to the left. Let's see what happens if I plug in an x value of -1. When I do so, I would get y is equal to -1 squared. Well, -1 times -1 is just +1. So what that means is that this point would be x value of -1, y value of +1. And already, hopefully, you can start to see that we're starting to slowly form what looks like a parabola. Let's check if that pattern continues. Let's try when x is equal to -2. -2 times -2 is 4. And would you look at that, at the x point -2, we have a y value of 4. I know that this will also be true for -3. We can check that when x is equal to -3. -3 squared is 9. And so there you go. You have matching points as well. If I wanted to extend this one further, I could. So I'll keep generating test points over here. If x were to be 4, then y would be equal to 4 squared, and in this case, y would be equal to 16. So y would be equal to 16 when x is equal to 4, and I know that that would be true for the other side of this equation. And so then what I would be able to do is connect all of the dots very poorly with my drawing tablet. Oh, it wasn't actually too bad. Good for me. And we can see that we have a parabola. And we can also see that our vertex here, let me just erase some of these little arrows here and clean that up a little bit. My vertex is at the point 0, 0. And there's a reason for that. And we're going to start talking about that throughout this lesson. That there is a reason that this vertex fell at 0, 0 when our equation was y is equal to x squared. There's a reason for that. So vertex graphing form, that is something that we are going to be using quite a bit more as we traverse through these lessons. Vertex graphing form has to do with this equation here. Y is equal to a times x minus p squared plus q. And we are going to define what each of these variables are, but in every case, y is just equal to the y value on the graph, and x is equal to the x value on the graph. And so what we'll find is that for every single x value, there will be a y value that goes along with it, and that will represent a point. So what we were doing with these test points here is we were trying to plug in numbers for x and then solve for y and figure out what the corresponding point would be. So we figured out that 0, 0, the vertex, was one of our points. We figured out that 1, 1, this point here, was another one of our points. P and Q are two new things that we are going to deal with, and I'll just give you a bit of a preview. All of the equations that we're going to graph today will be in this form of y is equal to a times x minus p squared plus q. All of our graphs will be in this form. We will not deal with a yet today. We will deal with a next week when we continue on lesson 2. As you can see here, a will determine the shape of the parabola. But for us today, let's define what P and Q actually are. So P, what P does is it represents the horizontal shift, and that is how far to the, I'm just going to make sure that this cuts off here. How far to the left or right the graph has shifted from x is equal to 0. And why I say x is equal to 0 is we said that this was the most basic quadratic function, and this one had the vertex at x is equal to 0 and y is equal to 0. And so when we add a p-value, that is going to shift the graph. Either it's going to shift this entire graph here. It's going to shift this entire graph here. Ooh, that was really, really poor. Let's try that again. Lasso select. It's either going to move the graph a little bit to the left, or it's going to move it a little bit to the right. And that p-value, whatever it is, will determine what direction it's going to shift. The q-value, can I find my spot? There it is. Copy this, paste this over here. The q, what that's going to represent is not the horizontal shift, but the q is going to represent the vertical shift. And so what that will do then is it will tell us how far the graph has shifted up or down from y is equal to 0. Again, we said with the last graph that we did there that the vertex was at the point 0, 0, where x was equal to 0 and y was also equal to 0. This p-value and this q-value will shift what direction our graph is going to go. One thing that is worth noting, notice that the p-value is subtracted in this form. And it's because we have x minus p. And the other thing we want to notice is that the q value is being added. So for us, if the equation was y is equal to, if the equation was this, y is equal to 2 times x minus 1 squared plus 5, then our p-value would be equal to positive 1, and our q-value would be equal to positive 5. So the negative sign that exists here, that's there before the actual p is. If we got a scenario, that looked like this instead, so if the equation was y is equal to 3x plus 4 squared, the value of p in this case would be negative 4, because it would be like us having a x minus a negative p, which would turn this then into a plus sign. So it would change this into a positive p. However, the p-value was still negative before we did this little erase step, and as such, that is going to shift our graph in the downward direction. So I guess kind of the basic things that we want to determine is from that little equation there, taken together, p and q values determine the vertex of the parabola. The vertex of the parabola. The values of p and q determine the vertex of the parabola. So in this first sample equation that we looked at here, the vertex would be 1, 5. That would be the vertex of our quadratic. In this second example, the vertex would be equal to negative 4, negative 6. All right. So that's our first little equation there. And all the background information that we need to know for going through this lesson. All right. So we want to fill in the characteristics for each of the following quadratic functions, and then we also want to provide a graph of the function. And I am going to use Desmos to help us graph the second two, but for this first one here, we're going to spend a bit more time, and I'm going to show you how you could actually go about graphing it and figuring out the x-intercepts, the y-intercepts from a mathematical basis. The Math Foundations textbook, when it goes through, it allows you to use a graphing calculator or allows you to use Desmos to come up with your solutions. Okay, so doing this first little question here, we are given f of x, and again I said that this was the same thing as y, those two are interchangeable, is equal to x minus 3 squared minus 4. For some of you, it'll be nice for you to label that p is equal to a positive 3 and q is equal to negative 4. Again, even though there's this negative symbol here, our p value is just this 3 by itself. If it was x plus 3, then this would be a negative 3 value. But because it is x minus 3, we know that our p value is 3 and our q is negative 4. So looking at this direction of opening, we said that that was determined by this x, whatever's in front of the x here. If x squared was negative, then it would be opening in the downward direction. If x squared was positive, it would be opening in the upwards direction. So I could actually FOIL this guy out here, where we have f of x is equal to x minus 3 squared minus 4. Many of you will be able to see that this x will remain positive no matter what, but I just want to show you that that is the case. So expanding this out, we have x minus 3 times x minus 3, subtract 4. You would need to FOIL this out, as I said, so it would be x times x, and then x times 3. And then with this negative 3, you do negative 3 times x, negative 3 times negative 3. And what you'd end up with here is you'd end up with f of x is equal to x squared minus 6x plus 9 minus 4. And you can simplify that down into x squared minus 6x. And we can combine the 9 and 4 because they don't have any x's, so they are called like terms, to x squared minus 6x plus 5. So again, we said that we wanted to simplify this expression, and we said the value of a positive or a negative in front of this x squared, we said it was a positive value, so we know that this parabola will open up. We also know the vertex just by looking at this equation. Because we have our p and q value, we know that our vertex will be 3, negative 4. In terms of finding our x-intercepts and our y-intercepts, there is an easier way that we could do this that we will do on these next two graphs here, but I'm going to show you the mathematical derivation of how you can find these x-intercepts. So we simplified our equation. So if we want to find our x-intercepts, we simplified our equation to be y is equal to x squared minus 6x plus 5. We know that an x-intercept occurs when y is equal to 5. So we have x squared minus 6x plus 5. In order to solve this expression and figure out how many x-intercepts we have and what they are, we would need to factor this. So I would need to think of two numbers that when multiplied together equal 5. And the only two numbers I can think of are a 5 and a 1. The next thing I need to decide is I need to decide how I can achieve just an x squared. The only way that I can achieve just an x squared is if I take an x and multiply that by another x. That's the only way I can do that. So I know for sure that I will need two x's, and the other thing I know for sure is that I'll need inside of these brackets a 5 and a 1. Now the last thing I have to do is I have to decide what sign I'm going to put in between these. Is it going to be x plus 5 or x minus 5? Is it going to be x plus 1 or x minus 1? And in this case, we would like whatever this multiplication is and this multiplication is to add to negative 6. So the only way that's achievable is if we end up with x times negative 5 or negative 5x and x times negative 1 or negative 1x. And then we would add those two together and say negative 1 minus 5x, negative 1x minus 5x would give us negative 6x. And then to solve this, we would need to find out what numbers I can put in for x in these brackets to have them equal 0. If either one of these brackets equals 0, then the entire expression itself will also equal 0. So I could plug in a positive 5 in this case, and 5 minus 5 would be 0. 0 times anything is 0. So that one would be one of my possible answers. And the other one here would be a positive 1. And that would mean that this bracket would equal 0, and it wouldn't matter what was in this bracket, it would also equal 0, because we're multiplying by 0. So I know that my two x-intercepts would be 5, 0, would be 5, 0, and they would be 1, 0. So I can mark those two actually on the graph. 1, 2, 3, 4. 1, 2, 3, 4, 5 right here. 1, 2, 3, 4, 5, 0, and 1, 0. And then I'll also mark my vertex, which is 1, 2, 1, 2, 3, 1, 2, 3, 4, right down here. So I've got 3 known pieces of information now. If I wanted to solve for my y-intercept, I know that my y-intercept will occur when x is equal to 0. So the opposite was when I solved for my x-intercept, I made y equal 0. Here I'm going to make x equal 0. Well, if x is 0, I have 0 squared minus 6 times 0 plus 5. Y is equal to 5. So I know that my y-intercept will occur at the point 0 for your x, 5 for your y. So 1, 2, 3, 4, 5, like that. My axis of symmetry, we said that this is always x is equal to, well, whatever the vertex was. In this case, it is 3. Domain, we said that that was always the same. It was always xer. And then the range, we said that what that will be is that will be always yer. And then dependent on what direction our parabola is opening and where our vertex was. So the other statement here is that y must be greater than or equal to -4 because we are opening in the up direction. One of the things worth noting is that with parabolas, when we go over one space, the y values are always the same. So for both of these 2 points here, both of our x-axes, that looks like a really surprised face there. For both of our x-axes, we've gone over 2 sideways spaces or 2 x spaces, and we have the same y value. So I could also map out this point, and I know that that would be true as well. We know that the vertex occurs at 3, -4. So what I would want to do is I would want to solve for some additional test points. And so we knew that the vertex was at x is equal to 3, y is equal to -4. So I just want to check and see, I want to check when x is 2, what is y equal to? And so I would plug an x is equal to 2 into my equation, and I would have y is equal to 2 minus 3 squared. What's the last part? Plus 4? Minus 4. So I would have -1 squared minus 4. This would be +1 minus 4, and then y would be equal to -3 in that particular case. So I could plug in the value when x is 2, which is right here, y is -3, and then I know that the axis of symmetry exists. I know that my axis of symmetry exists right along the middle of the graph, like so. And so what I know from that is I know that whatever is on the left-hand side of this graph will also be true or will be mirrored on the right-hand side. And so I can put a point there. And then I can connect all of these dots like so. And I have my parabola drawn. The last thing that I would probably do if I was working through this question myself is I would just confirm that that is what the graph looks like in Desmos. So y is equal to bracket x minus 3 bracket squared minus 4. And that looks exactly like what we drew. We have the same intercepts. We have an intercept of 5, 0, 1, 0. We have an intercept of 0, 5. And our vertex is 3, -4. So we know that all of those values were correct, and we know that they were all accurate, and we knew that we have drawn our graph correctly. Does anyone have any questions yet? Okay, awesome. So we're going to do these next two here. We'll fly through these ones. We have two similar equations. Again, what I would probably do is I would expand these out just to double check and ensure that your x is a positive value. But in both of these x plus 6 and x plus 1 squared, in both of these brackets, I don't have any negative values there. So I know that this x squared, whatever I generate, will be positive. And as such, I also know that this graph will open in the up direction. The other thing I know is I can go through and see that my vertex, this equation is given to me in vertex form. I know that this sign has changed to a positive value, which means that my p value here, this is p, and this is q. I know that my p value must have been actually a negative 6. And then I know that negative 9 will be my q. In terms of x and y intercepts, I would plug this into Desmos and then find those, but I do know what my axis of symmetry is. I know my axis of symmetry will be equal to whatever the x value of my vertex is, and in that case it's this negative 6. Domain we said is always xer. Range we said is always yer, and then we needed to look at both the direction of opening and the vertex. We see that this is up, so I know that y must be bigger or greater than or equal to negative 9. And so if we plug that equation into Desmos, we get y is equal to x plus 6 bracket. Ooh, I got lots of fun things going on here. Let's just clear this out. Y is equal to bracket x plus 6 bracket squared minus 9. And then we could check this graph and say, is this exactly what we had previously seen? I'm just going to insert a screen clipping real quick here of this graph. Insert that. Make it a bit smaller, and then we'll just drag it up here so that you have the graph right beside the actual equation. Okay, so we would check our intercepts then here and check our vertex. First thing I do is check my vertex is in fact negative 6, negative 9. Wonderful. I would then go through and check to make sure that this point up here is negative 9 comma 0. So that's one of my x-intercepts. So I go back to my little piece of information here, and I know that one of my x-intercepts is negative 9 comma 0. I'd go back and I would check this other x-intercept, which is negative 3 comma 0. And negative 3 comma 0. So those 2 points. Last thing I have to check is I have to check my y-intercept. And my y-intercept would be all the way up here at 0 comma 27. At 0 comma 27. And so we could graph all of those points once we had all of that information. I just took a screenshot of Desmos and included that in there, but for sure we could go through and graph it on this little graph. One of the issues that you would run into is you would run into the fact that if you wanted to show the y-intercept of 27, you only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You only have 10 spaces to somehow include a y-intercept of 27. And so what you would need to do is you would need to make each space worth 3. And so what that would mean is that this first point would be 3, 6, 9, 12, 15, 18, 21, 24, 27, and then this last point here would be 30. And so then you would be able to fill in all of the appropriate points to show that you know what your y-intercept is in that case. And then I would also do the same along the x-axis as well, making each point worth 3. So that's just a notation thing for you to be aware of. Looking at this last equation here, we have x plus 1 squared. Again, within that bracket, I don't see any negative values, so I know that my x squared, let's actually FOIL that one out. F of x is equal to x plus 1 squared plus 2. You could rewrite that as x plus 1 times x plus 1. And then we can ignore this little plus 2 for a while. Foiling that out, first I would do x times x and x times 1. So I would end up with x squared plus 1x. And then in the red, the second FOIL I would do would be 1 times x and then 1 times 1. And so I would end up with another 1x plus 1 times 1 is 1 plus 2, like so. And so you can combine all of your like terms. I only have 1x squared here, so it's just x squared. I can add the two 1x's together to end up with 2x, and then I have 1 plus 2. I end up with that expression there. So again, that just confirms that our x squared value, when simplified, is a positive value, meaning that this does in fact open up. Our vertex, again, we have this positive sign here in the brackets, which means we need to think about it for a second and say that our p-value must have been a negative value. It must have looked like this originally, x minus a negative 1. And then that would have been all in squared brackets. So those two would turn into an addition sign, meaning that originally my p was negative 1 and my q positive 2. So I can map that point on the graph already, negative 1 here, positive 2. That's my vertex, and I know it's going to be opening in the upwards direction. Immediately, I can fill in a couple pieces of information. Without really even knowing what my graph looks like, it could be really wide, it could be really skinny, I'm not sure. I know that this will never cross the x-intercepts. So my number of x-intercepts is none. I don't have any. My axis of symmetry, I can also solve for that. We said that that was borrowing the x value from your vertex, which was negative 1. So I then know that whatever is on the left-hand side of this axis of symmetry will be identical to whatever is on the right-hand side of this axis of symmetry, this gray line that I've drawn here. Domain, we said that that was always the same thing. Ooh, hello. Wrong button. Domain is always the same thing. We said that that is XER. And then we said the range is always YER. And then based on our vertex and what direction it opens up. So we know that Y must be bigger than or equal to 2. The only thing left to do here then is to find out whatever our y-intercept is. And we could do that using this original equation. We said that the y-intercept will be achieved. When our x value is equal to 0. So y is equal to 0 plus 1 squared plus 2. So y is equal to 1 squared is 1 plus 2. Y would be equal to 3. So I know that I would have a point that exists right there, and I'd also have a point that exists right opposite to it on the other side. So our y-intercept, we said that this was at the point 0, 3. From here on out, you could keep doing some test points if you wanted to keep graphing. So test points. I'm going to choose the x value that I don't yet know beside this here. So that would be an x value of, that's 0, that's the vertex. I'm going to choose an x value of 1. And then I would have y is equal to 1 plus 1 squared plus 2. 1 plus 1 is 2. 2 squared is 4. Plus 2 means that y would be equal to 6. So I would count up 1, 2, 3, 4, 5, 6. And then I would also know that that point will be mirrored on the axis of symmetry on the other side there. So I don't actually even have to solve for it. And then I would choose an x value of 2 just to get one more point in here. Y is equal to 2 plus 1 squared plus 2. 2 plus 1 is 9. 2 plus 1 is 3. Sorry, 3 squared is 9 plus 2. Y would be equal to 11. And I actually don't think my graph goes all the way up to 11. I think it goes up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 would be right about here. So now I'm actually exceeding the point of my graph. I probably wouldn't really even graph those points, but I'm going to include them for our little demonstration there. Connect all of those dots like so. And then we have a graph that looks like that. We will check this in Desmos where y is equal to x plus 1 bracket squared. And then we were adding 2 to that. And we'll just confirm that this graph looks identical. We have a vertex of -1, 2, which is correct, a y-intercept of 0, 3, and no x-intercept. So it looks like that graph was exactly as we had calculated there. Does anyone have any questions from today's lesson? Okay, awesome. As always, myself and Ms. McNee are completely available if you would like some help. What you should be finishing up this week is you should be finishing up the linear inequalities exam. You will get an assignment from this particular lesson. It'll be this assignment 3 that I will ask you to work on next week, and that will be what you hand in. And then the week that follows, you will be doing the associated exam with this entire unit. So you'll get a quiz at some point here, starting off next week. We'll probably do the assignment either next week or the week after, and then we will go from there.